All right, thanks for tuning in, everyone. In this webinar, we're going to take a look at how low production volume sheet metal bending jobs can actually be profitable. Typically, the largest upfront costs with a sheet metal gig are tooling related. I come from the automotive world where tooling costs are very prominent, particularly in the metal stamping and injection molding sectors. I bring this up because both automotive and sheet metal industries use the same solution to offset these high tooling costs by making a lot of product. That's one of the main reasons why cars like the Lexus LFA and Bugatti Veyron, each of which saw less than 500 units built, are so expensive. While these ultra-high cost performance cars have deep-pocketed buyers willing to fork over the big bucks, the same cannot be said for expensive, small, custom sheet metal orders. With most customers not willing to pay the high prices, the fate of these jobs usually end up the same way. But what if they didn't have to? Much of the high cost associated with traditionally manufactured sheet metal bending dies is just that. They were made with traditional manufacturing methods. Expensive blocks of steel that have to be milled down with expensive CNC machines operated by expensive, highly skilled machinists is, well, expensive. However, there is an alternative manufacturing method that can easily eliminate all these barriers. It uses strong, low-cost material in a comparatively less expensive setup that is fully automated, no tending to or programming required. And to build on this list of opposites, the name of this technology happens to be an antonym of subtractive manufacturing. Of course, we are talking about additive manufacturing or 3D printing. That's right. You can actually 3D print sheet metal tooling. In fact, we've done it before with our sheet metal stamping dies. And here, we did it again, only this time focusing on sheet metal bending. After speaking with Roland, our resident sheet metal expert and one of our top CAD AEs, two types of tooling were settled: a Z-bending die and a gusset forming die. To understand why we chose these, it's important to first understand that unlike injection molds or stamping dies, sheet metal bend dies can be used across many different jobs as long as factors like material and gauge are the same or similar. This is easy to do with simple V-block dies, but more complex bends and new or uncommon gauges require custom tooling. When presented with a job that will require new tooling, machine shops will first determine if modifying a pre-existing tool is possible. That way, less cost is incurred by the customer and turnaround time is shorter.
So for these dies, this is just a whole bunch of 1/4-inch pieces stacked up and welded together. Because if you've ever shopped for this stuff before, it is extremely expensive.
However, there are limitations to modifying dies, and that leads us back to the tooling we chose. Z-bending dies have unique geometry that is specifically designed to the size of the Z-bend and gauge of sheet metal. Therefore, there's no room for modification here. Gusset forming dies, on the other hand, are a little more forgiving because they're usually a V-block with drilled through holes for rod insertion. It's an easy modification, but it means drilling holes into a perfectly good V-block, plus you are now limited to forming gussets of one size. Not much room for modification, as it turns out. But none of these limitations need to exist when you have high-strength composite 3D printing at your disposal. Thanks to Markforged, custom dies can now be made both quickly and inexpensively. Before we get to printing, our dies first had to be modeled, a job accepted by James, MLC veteran and one of our other top CAD AEs. In fact, he went ahead and just modeled up the whole 20-ton press we bought. So yeah, I'm pretty sure he's just flexing his SOLIDWORKS skills at this point. But actually, it helped us get an understanding of how tall to make our dies and how to firmly secure the top punch to the post. On that second point, we pulled from a skill set that was the subject of a webinar from last year: 3D printing's unique ability to attach anything to anything. James applied this knowledge to model a ring that can slide around the press's post and features notches that engage with the punch. He even made the notch slightly deeper than the post so that the post is the one applying pressure on the die. With this work done, James could begin modeling the dies. The critical bits of information here are knowing the sheet metal gauge and any clearances to take into account between dies and mating components. If that all sounds familiar, it's because dies designed for machining or 3D printing undergo essentially the same design process. With FDM 3D printing, clearances are typically 0.1 millimeters for tight fits and 0.2 millimeters for loose fits. And as for the sheet metal, our primary gauges were 22 gauge and 16 gauge steel. Satisfied with the models, we exported the STL files for all the dies and imported them into Eiger, the slicing software for Markforged printers. Markforged printers are perfect for this application because they print with extremely strong thermoplastics capable of being reinforced with continuous fibers like carbon fiber. Their most common material is called onyx, a chopped carbon fiber infused nylon that is 1.4 times stiffer than ABS and is what we used here. If you pair onyx with continuous carbon fiber, by the way, you can actually achieve stiffness equivalent to 6061 aluminum. It's really strong stuff. But to test the waters, we relied on just onyx for the first die sets, boosting the strength by doubling or tripling the roof and floor layers and the wall layers. And with all this set, it was now time to print. Now we have two printers in our office, the Desktop Mark II and Industrial X7. We were able to crank these dies out in no time thanks to printing them on both printers. Everything was looking good on them, so all that was left for us to do now was squash some metal. Our 22 gauge and 16 gauge pieces were prepared by using our tin snips, which was brilliant for the 22 gauge steel, a Dremel, which was okay, but mostly just made a ton of noise and sparks, and a hacksaw, which made me pray for the sweet release of death.
Hallelujah!
The 22 gauge piece was thrown into the pinless gusset former and bent with the help of our coworker's 6-year-old son. Not trying to one-up anyone here, but if we can bend sheet metal with custom-made 3D printed dies and some child labor, then you can too. Well, minus the child labor part. And we'll continue to put the time and material cost in the corner of the screen for each die set, so look out for that. Oh, and to retract the bottle jack, you usually use the cranking pole to turn this relief valve, but this is a bit awkward, so James actually modeled and 3D printed this handle to make our lives easier. I'm telling you, 3D printing has so many uses. Back to the bending, we inserted a 3/16-inch cotter pin and laid down our 16 gauge plate, which is the gauge this die was designed for. It's a little awkward lining the two die halves together and keeping them lined up, so it takes a bit of finesse and patience. But the bending worked well and the gusset looks really clean. And speaking of clean, the bend lines appear parallel when placed against the 90-degree section of I-beam on the press, so that was good to see. Only downside was our cotter pin didn't hold up so well, but you can see here the die wasn't even scratched. We then loaded up some more 22 gauge stock and attached a digital angle reader to the plate. We bent it to a 45 degree on one side, 90 degrees in total, and lined it up to our press's I-beam. Thought this was kind of a cool demonstration of spring back. You can see the plate isn't quite parallel. So we threw it back into the die and squeezed it a little north of 47 degrees or 94 degrees total. And now it's looking much better. We ran those same numbers on the 16 gauge plate, and you can see that the thicker material doesn't exhibit as much spring back, so got it a little overbent here. Now with our cotter pin toast, James went back and reprinted the V-block to accommodate a 1/4-inch linch pin. We threw in our 16 gauge plate and sent it. The gusset now looks far more pronounced, and you can actually feel the greater stiffness compared to the gussetless plate. Next, it was time to test the Z-bending dies. We marked our 22 gauge plate with bend lines to make a hat channel and compressed one side. Then we flipped it around and compressed the other side. The part turned out flat, and the height of the hat channel was within 1/10,000th of an inch between the two ends. And I mean, considering we're using a 20-ton bearing press with floating upper and lower spans, I'm blown away that we are actually able to achieve this much accuracy. And since we had some time, we threw in a 16 gauge section 2. We had a bit of rocking on the top die that resulted in some duller bends in comparison, but I think it turned out satisfactory, all things considered. Even after all this tonnage and compression, the Z offset dies are not showing signs of damage. Now, we were walking down Easy Street at this point and wanted more of a challenge. We saw some 1/8-inch steel flat bar at Home Depot and bought some. James went to town in SOLIDWORKS to configure a new V-block and punch capable of bending this behemoth. The same slicing process you saw earlier was applied here, and the job was sent to the printer. Loading the dies into the press, it was time to cut a piece of this thick flat bar and mark the center of the bend. Then we began pressing on it. You'll immediately notice the punch begins to tilt. With more and more pressure, the plate is bending, but the punch's angle is also growing. I wonder what'll happen. Honestly, that scared the shit out of me. The tilted punch was placing so much lateral pressure on our punch adapter ring that it delaminated along the layer lines, sending everything flying into the wall. I'm just glad it took a chunk of sheetrock out of the wall and not out of me or James. The punch and V-block both saw compression damage, so it was time to reset. James went back into SOLIDWORKS and decreased the angle of the V-block and increased the radius of the punch to reduce the tonnage required to bend the flat bar. It's so easy to just go in and change dimensions in parametric. You gotta love it. Also, a hole was added in both the ring and punch to allow for a 1/4-inch bolt to pass through. This would prevent the rocking we saw on the punch and stiffen the ring to prevent delamination. We resliced the parts, keeping the punch's parameters the same as previous, but the V-block was updated to include continuous carbon fiber reinforcement. With the V-block, we have both compressive forces and lateral forces, so we used 2 fiber reinforcement strategies. Isotropic sandwich panels were added just beneath the apex of the V and at the bottom floor to resist the downward compression, while striped concentric fiber rings were added along the V to resist those lateral forces. We could have added them in one uninterrupted group, but striping is more material efficient without sacrificing much in the way of strength. The parts were then reprinted, and the next day we couldn't wait to come back to work to test. Now, for the sake of brevity, we didn't show some of our other attempts to bend this 1/8-inch bar, but we had a couple other V-blocks printed to help gradually bend the bar further and further. With each new V-block, James reduced the V's angle, performing what's called air bending in the industry. Now, of course, as a millennial, only one thing comes to mind when I think of air bending, but the more air we had, the sharper we'd get the bend. And the sharper it became. Eventually, we got to within a few degrees of 90 and decided we gotta get it just perfect. As we were bending the bar more and more, again, that scared the out of me. The V-block had so much lateral force that it began pulling up on the layers beneath the V's apex, resulting in delamination. James and I discussed increasing the width of the block or adding ribs along the sides prior to printing, but all things considered, I'm just really impressed with our efforts. The bend lined up with the press's I-beam and is within a degree of 90. So that pretty much covers it. Here are all the dies we made along with all the sheet metal bent. To think how quickly we could just drum up a new version, bend some pieces, iterate where needed, and to do it at an extremely low cost just boggles the mind, especially when you think about how it compares to traditional methods. And when you think about areas where we may have lacked some success, imagine if we had a proper press break and we printed our dies solid, or if we increased their thickness, or maybe if we added more fiber. Not only would we be cranking out sheet metal parts left, right, and center, but we might be able to bend up to 1/4-inch plate. In fact, maybe that'll be the subject of a future video. I keep saying that after each one of these, and a new project always comes up, so I guess we'll just see how far this sheet metal series takes us. But that's all from me, and I appreciate y'all for watching.